So an abstract for this talk, trees were introduced in version 12.3, and they represent rooted, ordered, labeled trees with leaves. In this talk, I'm going to be talking about the new features added since last tech conference, that's version 13.1, and a little bit of what's coming up in version 13.2. Main things are new ways of constructing trees, like trees with associations, XML and JSON. Also going to talk about new visualization options and functionality that's available, and finally some new functional programming operations that are available for trees. So to start with, seeing how to represent trees generally. So trees represent rooted, ordered, labeled trees with leaves. So here's an example of what that looks like. This is a tree with 3 leaves, which are the numbers 1, 2, and 3. So if I evaluate this tree, get this tree here, and you see there's the root node with no data, and then 3 children, 1, 2, and 3. All non-leaf nodes can also contain data, not just the leaf nodes. So the way that's done is by giving an optional first argument to tree. So if you do tree of 0, comma, this list, evaluate that, there we see we get a similar tree with 3 children, which are the leaves 1, 2, and 3, but now the root node additionally has this data 0. By the way, is this big enough? The final thing about representing trees is that these things can be nested. So in the list where you can have expressions representing leaves, you can also include tree objects, and those will be the children. So to see what that looks like, here we have 2 children. If I evaluate these in place, I see there's the first tree, there's the tree with 4, 5, and 6. So now I have a tree object with a payload and a list of subtrees. If I evaluate that, we get that tree. Now, new in version 13.1 is the ability to name branches in a tree, and the way that's done is by using an association. So this tree here will be very similar with 3 leaves, which are the numbers 1, 2, and 3, but this time, since the children are given in an association, the branches will have names, in this case, the symbols A, B, and C. Evaluate this. We see we get a tree with 3 leaves, and the branches are named A, B, and C. So this is very useful for several different kinds of trees. For example, data sets. So here's an example data set of the planets. We evaluate that in place. There we see the typical data set formatting with all the various keys. We can convert that to a tree using expression tree. So if I do expression tree of that data set and specify data set in the second argument, we will get a tree representation of this. So there we see the root node, the branches are the planets, they have keys for their mass, their radius, their list of moons, and so on. So once you have a tree with an association of children, you can use the keys in the association to reference the positions of subtrees. So here's an example of extracting the mass from every planet in the data set. Do tree extract of that. There we see the masses of the planets. Version 13.1 also added the heads option for converting arbitrary expressions into trees. So now you can control whether you want the head to be included as a subtree by specifying heads arrow either true or false. So this is these structures here, heads, sub-expressions, and atoms, also the versions that hold the sub-expressions. So if we take a look at these, doesn't appear great in this, but you can see the heads tree. You have the head of the expression is plus, then you have today plus 1 days. The held version, the symbol today is held, and you can see in the second row here, this is with heads goes to true, and you can see there's a leaf node for the plus. And this is similar for all of these. So here you can see The head plus is included. In the top row, it's not. Another new representation that's available in version 13.1 is the ability to convert XML into a tree. So here I have an XML string representing the sales of various famous paintings. So we have the paintings tag. Within it, you have these elements with the tag sale. So we have several sales. Each sale contains a title, an artist, a year, and so on. So we can import this XML string into the Wolfram language using import string, and we'll see how that gets represented. So here we have symbolic XML in the Wolfram language. You can see the entire XML document is given as an expression. The head of that expression is XML object document. Then within that document, we have all of the nested elements. So here's an example of one of the sale elements. There you see the tag and the nested elements. So now in version 13.1, we can take this symbolic XML and produce a tree from it for further processing. So here's how that's done. You say expression tree, giving the output and saying convert that to an XML tree. So we evaluate that. Here we can see this tree has been converted. So we have the root node, the body is this paintings element, and then within it, all of the sub elements. We can use all of the visualization options for trees on XML trees. So here it'll be an interactive outline view of the tree using tree outline. So we say tree outline of the tree. This is specifying which positions will be open initially. So we evaluate this and see what that looks like. And now we see the XML tree has been rendered as an outline. I've got this sale and this sale opened to the title and the year. You can close elements of the outline. You can open other elements of the outline. So that's very useful for visualizing large XML trees interactively. Another important tree representation is JSON. Wolfram language actually has two ways of importing JSON. So the first I'll show is by representing JSON objects as nested lists of rules. So here's a JSON string representing some information about chemical elements. See what that looks like normally. Similar to XML, you can import a JSON string into the Wolfram language using import string. So we do that. We see this is given as a list of rules, and the right-hand side of the rules, the values can themselves be lists representing nested JSON objects. This can be converted into a tree, again, using expression tree. So we say expression tree of those nested rules and say JSON in the second argument, and we can see what that looks like. So here we get a tree. So the root node represents the entire JSON object. Its children are the keys in that object. Then the children of those nodes are the values, which in this case are again, further JSON objects. So we can see hydrogen with its atomic number and atomic weight, same with helium and lithium. Another way that JSON can be imported into the Wolfram language is as nested associations. So that is done by using the import-export format raw JSON. So if we import that same JSON string, this time as raw JSON, instead of nested rules, we'll have, nested lists of rules, we'll have nested associations. Here, very similar. Now we have an association representing the JSON object, and the values are, again, nested associations. So if we convert this to a tree using expression tree, specifying raw JSON, we can see the difference that this makes. So now rather than the keys of the objects being their own nodes, the keys of the objects are just the keys in the tree giving the names of the branches in the tree. Just wanted to point out that both JSON and raw JSON support arbitrary JSON objects and arrays. So here's a mixture. This is an object that contains another object and an array. So look at that side by side, and we can see this object, on the left, this is using nested rules, and you can see the keys have their own nodes. On the right, the keys are used as the keys in the tree. And here is the list 1, 2, that's an array. And we see that array also in the raw JSON representation. Moving on to styling, we added these options, tree element label and tree element style, that allow you to control the labels and styles for the nodes in a tree. Let's look at an example of that. This is that XML tree from before, and I want to say, make all of the sale tags light red. So that can be done by saying tree element style, tree cases of sale goes to light red. Take a look at that. Right, so here's the XML tree, but we've now highlighted all of the sale nodes, the nodes with sale tags, as light red. An example with JSON and using tree element label. So reevaluate that. So here's this JSON tree, and say I want to label these nodes here with the atomic symbol for their parent. So I say tree element label, and in an association, positions are given using their keys. So for the key hydrogen, we're going to use the label H. For helium, we're going to use HE. And for lithium, we're going to use LI. I think those are correct. Evaluate that. And there you see the node for the branch labeled hydrogen now is labeled H, and so on with HE and LI for helium and lithium. In version 13.1, we expanded these options to include the ability to control every aspect of labeling and styling for both nodes and edges. So this is a kind of involved example of that. We're going to use all of the various vertex shape functions that are available, one for each node in the tree. For the edges, we use the option parent edge style function. So the function version of this option takes a function that acts on the data. So here, the style for the parent edges are being computed by taking the data in the node and dividing by 100 and representing that as a hue. Similarly, you can control the styles for the nodes as well as the edges using the tree element style function. And this is similar. And there's also things like little functions, shape functions. So this is using the function Roman numeral to generate the labels. So in this example, we'll get a tree. Each node is one of the different possible shape functions that are available. And the styles for the parents and for the parent edges and the nodes have all been computed from the data in the nodes. And you can see that the nodes are labeled using Roman numerals. We also added a function, unlabeled tree, similar to the function undirected graph, that can remove directed edges from a graph and convert them to undirected edges. Unlabeled tree will remove all of the labels from a tree. So if I do unlabeled tree of that XML tree example from earlier, here we get just an overall picture of the kind of structure of the tree without seeing any labels. Yes. Moving on to elision, sometimes trees can have many nodes. So one of the ways that we are improving this is by limiting the number of children that are displayed at a node by default. So here's a tree that has 15 children, and by default, only the first 10 will be displayed. So if we evaluate this, we can see what that looks like. So we see the first 10 children, and then finally this elision node saying there were 15 total children of that node. In version 13.2, we added an option to be able to control this behavior. So say if you wanted to display all of the children, you can specify max children goes to infinity. So this will be the same tree, but now you'll actually see all of the children for that node. Another way that you can control that is by using this global variable $max displayed children. So if you set $max displayed children, that will use that as the maximum number by default for all nodes. Let's see what that looks like. So I'm going to set $max displayed children to 2 and evaluate this tree. Here's the same XML tree from before, but now we get a more compact visualization where the remaining branches have been elided. Bob? Right, not currently. That's an interesting suggestion, though. Kind of like short. Yeah, kind of like. We'll have the elision in the middle versus the end. Yeah, yeah, that's a good idea. Make sure that if you set $max displayed children, you unset it to get back to the default behavior. Some new properties and measurements that were added for trees. One is root tree. So this is another function that's useful for exploring large trees. You just give root tree with a single argument, it returns the root node of a tree with all of its children removed. Say root tree of the XML tree, you see the root node is this node representing the entire document. You can also give levels in root tree to kind of walk down from the root, viewing just the top of it. So if I say root tree of the tree, comma 2, that will go down to level 2 of the tree and remove all of the lower levels. So if I do this, there you see we've got the root node, we went down one level to the paintings, we went down another level to the sails, and then the children of the sails have been removed. So the second argument has to be an integer. Ranges of levels aren't, I guess, meaningful for this operation since it always starts from the root node, if that makes sense. So, yeah. So there's this function tree level may do what you want. So you can give any level spec you want in tree level. So there I get just the nodes at level 2, or you could do a range of levels. Or if you just want the data. So let's look at an example of root tree with a negative level. So level -1 is all of the leaves of the tree. So if we ask for root tree down to -2, that will just remove all of the leaves from the tree. If we do that, here we get this tree. And now we go down to all of these nodes, but their values have been removed. We also added the function tree leaf count that gives the number of leaves. So that's the number of nodes at the bottom of the tree. We do tree leaf count of that, get 21. Finally, some functional programming operations that are available for tree. We have tree map and tree scan, which by default apply an operator to the data in a tree. If I have tree map F over a tree, what this is going to do is apply this operator F to every node in the tree. So we should get F of A, F of B, F of C, and F of D. Evaluate that. There we see the new tree we get, F of A, F of B, F of C, F of D. Tree scan is a variant of tree map that, like map and scan, it applies an operator to the data in a tree, but it doesn't return a result. It doesn't build up a new tree to return. So if I want to just traverse this tree and say print out the result of applying an operation, I can do tree scan. So I'm going to do tree scan of this operator composed with echo to print out the result. In version 13.1, you can also specify all kinds of new elements to apply to. So by default, the operator applies to the function, to the data. This will instead apply the operator to the original subtree. So let's see what that looks like. So there we've gone through this tree in a depth first traversal and printed out F applied to the subtree as we visit each node. The other thing we added the ability to do is to give multiple elements of a tree to the operator. So that's using this notation. So we're going to use the level spec all. So every node in the tree, we're going to apply an operator to both the data and its index and its list of siblings. So this function is just basically taking the tag and returning the tag together with its index. So if we evaluate this, here we can see a tree where all of the nodes with tags in them have been replaced to now be a list with the tag and the index. And you can see index 1, index 2, index 3, index 4, and so on. So it was a quick overview of the new functionality in 13.1 and 13.2. For the future, we're going to be adding many more conversions for constructing trees from different kinds of things available in the Wolfram language, like notebooks, structured text elements, code parse trees. We're going to also keep adding new functionality for extracting and transforming data in a improved visualization and improved interactivity, and also integration with the Wolfram compiler. That's my talk. Thank you. Yes. So if I want to do So for example, you can say all goes to subtree. It's kind of hard to see. Let me do original subtree. Right, so if you specify the level spec with a rule, you can say what element you want to feed into the function. So if you say original subtree, the function will be applied to the original subtrees. If you say subtree itself, then that's applying, let me do root tree of this. Tree data. Right, so this, if you say subtree, then you apply the function to entire subtrees and continually apply the function to the new subtree as it gets modified. One limitation of this is that the shape of the tree always stays the same. So this is modifying the data. We do want to be able to actually rewrite the structure of the tree though. Yes. No, you use tree cases. Let's take this example. Yeah, the XML example. Tree cases, XML tree. You can say sale. And that'll give you the list of all of the subtrees matching that data. Yes. Sometimes label or mm-hmm. Right. So does short work on strings? Okay. I don't know if there's functionality to abbreviate the labels as such. Using like tree element label function, you could do something like, string take 10, right? So if your labels are strings, you could specify a label function to shorten them. Yes. Mm-hmm. I'm kind of interested to see what your workflow for that is. If we have structured things like XML and JSON, we have converters for that. Just building up your own tree, I'd like to see kind of what your process is, and I could give more suggestions in. Yep. Mm-hmm. The tree line? Yes. Yes, so you may have heard of XPath and XSLT. So those are kind of languages for rewriting XML trees, and we want to be able to do the same kind of operations there. Yeah. Mm-hmm. Yes. So tree outline is kind of the first step for that. So tree outline is this thing that lets you kind of interactively open and close branches. We do plan on developing something for the standard visualization as a graph so that you could explore the graph interactively and click through the different nodes and collapse them. Yeah. Mm-hmm.
Can I choose a particular leaf in a large tree like formatting half of the leaf?
Should be possible. So let's try to do it live. So you can actually use graph functionality on trees and it converts them into a graph, but you need to use like tree cases, those functions to remain a tree. So what was one of them? Okay.